Inequalities, writing, graphing, and solving. The first thing we want to do is just review our inequality symbols. So do you remember less than and greater than? All right, less than points left, greater than points right? So I just keep in mind less than left. And of course we have less than or equal to, greater than or equal to. So now I just want you to go ahead and try. Connect the underlying words with what symbol you think should go in the spot. There are a couple of tricky ones, so I really want you to come back and check your work. Pause. Is less than. So of course that's less than, points left. Is less than or equal to. Okay, we started you out easy. Is more than. Can't be 50 then, it has to be more than 50, so just greater than. Is at most 50. Here's a tricky one, at most 50. So can it be 51? No, because at most 50. So less than, but it could be equal to because at most. Is no more than 50. Is no more than 50. So once again, we have this less than or equal to. Because can it be 51 if it's no more than 50? Is greater than or equal to, okay, we're back to just being nice and easy, and the product of 7 and a number is at least 50, at least. This one can be tricky, at least 50. So it can be equal to 50, but it has to be greater than that. 50, 51, 50.5, any of those.
Okay, after that intro, let's look over here at number 2. Graph each inequality on the number line. Okay, so here we have A is x is greater than 6 because greater than points to the right. And then for B, we have x is less than or equal to 6 because less than points to the left. So if I want to graph this solution set, what I'm going to do is I already have these nice number lines sitting here for me. So I want to show that x is greater than 6 on this number line. So the first thing I do is I go, okay, 6 is right here. If x is greater than 6, can I be equal to 6? No. So the way we show that on a number line is we put a big giant open circle right there at 6 to show that, okay, yeah, we're sitting here, but we are not equal to that. So you can put that directly on the number line if you want. I'm a little bit sloppy, so I always put mine above to make sure that it's clean and clear. Whatever you do, you want the person looking at your solution to know what's going on. So if you want yours floating or on the 6, up to you. Okay, so now that I've shown, okay, well, x is greater than 6, all I've shown is that I'm at 6 here. If x is greater than 6, it could be 6.5, could be 7, could be 100, whatever. So that's gonna be this direction. So I'm gonna draw this ray pointed to the right to show that x is all of these possible values here shaded on my ray. Moving on to B, we have x is less than or equal to 6. Okay, well, we're at a 6 again, so 6 is right here. This time, since I'm less than or equal to, I can draw my circle shaded in. Again, making sure the circle is obvious, okay? So don't draw me a little dinky dot. You want a obvious circle sitting there to show, yes, I am equal to 6. And then if I'm less than or equal to 6, well, I could be 5, I could be -5, I could be -1,000, who knows? So that means I'm going to point here to the left. So as I draw this ray pointed to the left, that means that x is all these possible answers here and 6, okay, because I'm less than or equal to 6. Now, I want to also point out, notice my obvious arrows here at the end of my rays. X could be anything less than 6, so that means that this ray could keep on going all the way to -1,000,000 if it wanted to, so that's why we draw those arrows there. Let's see if we can use this to solve some inequalities.
Next, we want to solve inequalities. One thing that we do need to remember, though, is when you multiply or divide by a negative number, you must switch that inequality. So if it was a less than, you're going to switch it to greater than, and vice versa. And let's take a moment to write this down, because when we write things down, we remember them. All right, did you get that down? Once again, super important, not when you're dividing by a positive, not when you're subtracting, only when you multiply or divide by a negative number. Let's look at A really quick. 4 times the quantity x minus 7 greater than -20. So we could divide out that 4 right now, and that seems like a really good idea because it goes into that -20 nice and even. I get an integer answer there. But of course, it's the same thing if you chose to distribute the 4. Remember, 2 ways will get there. At this point, we have to use the addition property of equality, add the 7 to both sides, and we end up with x is greater than 2. And now to graph. When you're graphing your own, just make a quick number line. Make sure and put the 0 in place, 1, 2. We're going to expect that to be marked at a minimum. And then it's greater than but not equal. So of course we draw in a swimming pool to show that it's at 2 but not equal to 2. It could be 2.001, but it can't be 2. And then greater than, so I'm going to shade the number line greater than to the right and put an arrow on to indicate, of course, that it can go on forever. Now I want you to pause the video, try the next 3, and then just come back really quick and check your answers. I believe in you.
All right, let's see how you did. The first one I'll go over a little bit closely, and then the next 2 I'll go through faster. So as the first one, the first thing I'm gonna do is distribute because I have those parentheses there. So I'm gonna have negative 6x minus 10. I'm gonna combine like terms, negative 6x minus 14. It's greater than or equal to negative 2. Add the 14. Okay, here's the crucial step. This is where you can either make a really big mistake or be totally on the right track. As I divide by this negative 6 here, I should have an alarm going off in my head. I just divided by a negative, and look at, Ms. Peart wrote about this. Anytime we divide or multiply by a negative in an inequality, we have to flip that sign. So I'm going to write x is less than or equal to, instead of greater than or equal to now, negative 2. Do not forget to flip that inequality. So now the number line, I'm gonna make sure I have 0, get my negative 2 on there. It's less than or equal to. Less than, left, done. All right, so let's look through C. The first thing I did was distribute, and then I subtracted my 3x, and something weird happened. Oh my gosh, I got 9 is greater than or equal to 6, and there were no more x's involved. Is that true? Is 9 greater than or equal to 6? Well, greater than or equal to, only one has to be true. 9 is greater than 6. Yeah, it's not equal to, but it's greater than. So this is actually a true statement, and it's always true. 9's always greater than 6. So what do we do when something's always true like that? Since 9 is always greater than 6, that means no matter what number I plug in for x, everything's going to work. So x is all real numbers, so there are infinitely many solutions for this one. Well, what's that gonna look like on a number line? If x is all possible real numbers, there's infinitely many solutions I could graph. So I'm gonna still label 0, but when I go to draw my ray, now it's gonna be like just this big line where I'm gonna shade the entire number line to show that every possible value would work for this inequality. Okay, as we look over at D, the first thing I did was combine like terms on that left side and then, get my x's to one side, and that's where, yet again, something weird happens. I end up with 4 is less than 4. Is that true? Is 4 less than 4? No. So this isn't a true statement, so this is almost like our no solution situation with equations. So I'm gonna say, like x, there isn't a possible x I can plug in and satisfy this inequality, so I'm just gonna say no solution, which means I don't actually have a solution to graph on my number line.